Okay, we're going to take a look at defining a fraction. And first we're going to start off with our number line. So I want you to draw a number line on your paper. And I've already kind of started one here. So we agree that in order to have a number line, we have to start with our number line, have a 0, and then we have to define, just like we talked about, we have to define what unit we're going to use. In this case, our length is from 0 to 1. Obviously on your paper it's going to be a little bit different, but make sure you copy it as equally as you possibly can so that the next line segment, so if this is the length from 0 to 1, then this is the same length from 1 to 2, and the same length from 2 to 3, so on and so forth, so that we've defined our number line as equal segments. 0 to 1 is the same as 1 to 2, so on and so forth. Okay, so that's how we define a number line. So let's take a look at this, and let's say suppose we want to partition. We've talked about partition and composing. Let's talk about partition. So if I want to partition the first line length from 0 to 1, let's say I partition it into 3 equal parts. So here's 1 part, 2 part, 3 part. If I keep doing that, I take the next line segment and the next line segment and so on and so forth, then I get a number line that looks similar to this. So we've taken our initial line segment 0 to 1 and we've partitioned it into 3 equal parts. Okay, so we've divided it, pretty much is what we've done. Alright, so that means if we do the next one, I'm going to continue on, but I'm just going to go ahead and recreate this. So if we have our line segment and we've partitioned each of those segments into 3 equal parts, then what we're saying is this length of the line segment is the same as maybe this length of the line segment, which is maybe the same as this length. So any of these lengths, even though it might not look like it drawn, but you can abstractly in your mind know that we have defined that each one of these line segments, doesn't matter which one we're talking about or where it is, these are all equidistant. Alright, so let's go ahead and, if that's the case, then let's go ahead and do this. Let's say that we have our partition into 3 equal parts, 3 equal line segments. Okay, so we're going to go ahead and we're just going to identify this first line length. So we did the same thing, except this first one is now the line length of 0 to 1/3, which means that the name of this first line segment here is 1/3. Okay, so if this is a line segment, we've just identified it as the length of 0 to 1/3, then each one of these is 1/3, 1/3, 1/3. Okay, so now if we have a collection of these, let's go ahead and go to this next one. So if I've taken this and partitioned it into 3 equal parts, if we take what we did, we can identify these again as 1/3. So here is 1/3, like we just said, this is 1/3. But this is also 1/3. This is 1/3. If I put these together, it's another 1/3, and let's just do one more. So let's say this line segment. Well, now we have 1/3, 1/3, 1/3, 1/3, 1/3. So what we have is 5 copies of 1/3. So 5 copies of 1/3. Alright, so it doesn't matter where they are, but I've got a collection of these 5 line segments that we've identified as 1/3. So what that means if we put those all together, so let me do this again, partition this into 3 parts. So if I take all those and I squish them all together, so here's the first one, this would be the second 1/3, the third 1/3, the fourth 1/3, and the fifth 1/3. Now I have a line length of 5/3. So this is the distance of 0 to 5/3. So I have that collection of 1/3 that were kind of scattered all over the place, but if I put them all together, now I have identified or defined the distance from 0 to 5/3, which is going to put me right here. So let's talk about the definition of a fraction. So fixing a whole number, n is greater than 0. So obviously if we don't partition anything, we don't have any partitions. So we divide the unit segment into n parts of equal length. That's what we did. In this case, we did it by 3. Then the first division point to the right of 0 will be denoted as the first partition. So in this case, it was 1/3. It could be 1/9 if we partition it 9 times, or 150 if we've partitioned the unit segment into 150 partitions. So the multiples of 1n then form the equal space sequence associated with n. The totality or total of all these points in the sequence as n runs through 1, 2, 3 is by definition the collection of all the fractions. So we had 1/3. Well, obviously the next one after 1/3, the second third would be 2/3. The next third would be 3/3. And the next one would be 4/3, and so on and so forth. Okay? So this brings up some interesting things. What if I have a number, and I'm going to call it L, and I multiply it by another number called M. Again, we have to define these, we have to quantify them, over L. So let's say that my partition, then what I end up, it's going to end up equaling this M right here. So for example, if I have 1/4, but I multiply it by 4, so if I have 4 copies of 1/4, then I'm going to get 1 in this case, because if this is M, then this is going to be 1. If I have, for another example, if I have 2/2 and multiply that by 3, then I'm going to get 6, or I'm going to actually get 3 there. Let me erase that. Alright, so if I have that, then I have 2 copies of thirds there. I'm still going to get 3, because whatever my partitions are, I have 2 of them, so I get 3. Alright, another thing that this brings up is if I have M over 1, so let's say our unit segment hasn't been partitioned, then however many copies I have of that, I'm still going to get M. So for example, if I have 5 copies of 1, then I'm going to get the number 5. If I have 99 copies, but I still just have my unit, then I'm going to just have 99 of those units. Alright, the last one is if, and again I can use any symbol, but let's go back and use, let's say B. So let's say I have a number B and I partition it B times. Well, B copies of B is going to give me 1, my unit. So for example, if I have a partition of 19, but I have 19 copies of those, then I'm going to end up at my unit, which is 1. I'll make that look like a 1. Okay? So those are some things that we can do with fractions, and some that happens with fractions if you take these whole numbers. Remember, we've just quantified these all as whole numbers. Then this is what will happen. We've got some examples here. Alright, so a number M in the fraction M over N is called the numerator of the fraction. So the M is the nth multiple of the fraction represented by 1 over N, so that's our partition, where N is greater than 0. Remember, you can't have 0 partitions, so N, whatever our N is going to be, has got to be greater than 0. All right, so for example, if I have 11 fifths, okay, here's our m over n. 11 is my numerator, and it's saying, what it's saying is that it's my 11th multiple. So it's my 11th multiple of 1/5. So it's 11 times 1/5, and again that gives me, if I turn that back into 11 multiples of 1/5, is just 11 times 1 is 5, so it's 11/5. Okay? Also, we can say that m over n is the concatenation, okay, remember that word, concatenation, of all the segments of 1n. So I can say 1n plus 1n plus 1n, keep going, and that is for m times. So what we have, if I want to use an example, is 1/4 plus 1/4 plus 1/4. Well, that's the same as saying 1, how many times? Remember, repeated addition is the same as multiplication, so 1 times 3, which is 3/4. So that's where the concatenation comes in. So it's concatenation if we're adding these all together, and if you go back to that number line at the beginning, that's what we did. We kind of put them all together, added them all up, and this gives us our multiple. So in essence, what we can say is m over n, this is kind of our summary, is m copies, and copies is like times, of 1 over n. So that is going to be our definition of what a fraction is. If you know that whenever you see a fraction like 3/4, you need to know that it is 3 copies of 1/4. Okay? And we'll talk about this more in class.